RISAFoundation utilizes a comprehensive set of modeling tools for the simple creation of a variety of foundation elements, including retaining walls, spread and combined footings, piles, and mat slabs. In this video, we will look at the tools that make designing a mat slab easy and efficient. To get us started, I've got a mat slab foundation already drawn here. It's got some loads applied in various categories. These could have come from an integrated model with RISA 3D. I could have put these in by hand. Either method works just fine. I've also taken a stab at the overall size of the foundation, just a preliminary guess, and we're going to take a look at the tools that I can use to get this design dialed in and finalized. I've already also set up the load combinations here, both for strength and service design. So I am ready to hit solve on this model and see what happens. Very quick solution here. And I get some warnings that a few points have exceeded the allowable bearing pressure. So let's investigate and see what is going on there. I also recommend checking out in the results spreadsheet list over here the slab stability spreadsheet, and this is going to give you safety factors for overturning. I scroll through that and I can kind of see at a glance that everything is fine. And next to that is sliding, and if I scroll through those, I see some safety factors in red that are less than 1, or my prescribed safety factor, that are jumping out at me as a problem that needs to be addressed. But let's see what we can do about that soil bearing failure. I like to open the soil pressures results spreadsheet. Now, this is a very long spreadsheet, which seems odd because I don't have that many nodes in my model that I placed. Most of these nodes are internal nodes that are generated when the slab is submeshed. So the soil bearing values that I'm looking at in here are all over the inside and the outside of the slab. I like to take the soil pressure column, right click and sort to maximum to minimum. And I can sort of see at a glance here that it's not too far over my allowable bearing, so that's good. And I've got the maximum load combination, the controlling load combination in all the failure cases, that one's exactly at 1, are in the 48 and 51 load combinations. So let's go and determine exactly where in the model these soil bearing failures are occurring. I'm going to turn off my loads for clarity. And up here in the quick view options, I have a variety of options for slab contour diagrams. So you can show the envelope situation here. I prefer to look at it as at combination by combination. And if I recall correctly, there was a soil bearing, switch this back to soil pressure. There's a soil bearing failure in load combination 48. Again, I can flip to my plan view and sort of see where that's occurring according to this color-coded legend up here. I see that, yes, it's happening on the upper left-hand side. And I also see that there is a area of 0 contact pressure happening just on the edge over here. So if that's something that I want to address, this will also indicate that that is happening. I had one other load combination that was failing, so I'm going to open up a second 3D view by way of the View tab here. I can snap that view, have these two side by side, and let's go turn on the same option for the other failing load combination. If I go through, I believe it was load combination 51. I'm looking at the shear values. Let's change that to the soil pressure values. Okay, so it looks like these are two different wind directions. So I've got failures on both sides of my slab. Seems to me like I could increase the size of this all the way around. Let's go back to a single view, set it back to the default view settings. I'm going to also turn my display grid back on. So there's a number of ways to edit this slab. We see here that I have an offset distance tool where I can simply increase all the way around. That would be easy to do. Let's say though that I have something limiting me on my left-hand side here and I don't want to use that. I can also redraw individual edges. I can remove edge points, or I can simply delete the entire slab perimeter. Let's not do that. But the slab is controlled by these nodes. I can simply drag them into place if that's going to be the easiest thing to do. In this case, I think it might be. Let's see what I can do here to get this scooched out a little bit. Maybe I want to bring this node down to here, bring this node in line with it as well. I can do this by way of the move command. I also want to move the outside nodes of the area load that was being defined. Let's put those on the sides there as well. And maybe I have decided not to cut this corner up here. I would like that to just be a right angle. I can simply remove this edge point without needing to delete or redraw the entire slab. I can also delete the node by simply hitting delete on my keyboard now that it's unattached. And then I can simply bring this node up to that point. Now I've got something that I think has a better chance of working. Also, if I click on the slab, select it, all the properties that I input before pop right back up. And let's say I want to change the thickness to 30 inches. I can also find all of these properties from within the slab's data entry, or from the slab spreadsheet under the data entry file here. All right, let's try that, see if it works. I'll just run the same solution. I don't get any bearing failures. That warning that I saw before didn't pop up. I can double check that by going into the soil pressure spreadsheet and finding that yes, indeed, nothing is exceeding the allowable bearing. And again, I'm going to want to check the slab stability ratios as well. Overturning, sliding, nothing in red, nothing jumps out at me. Great. Now that we've got the slab size dialed in, we can take a look at the reinforcement design. So I'm going to find information for my reinforcement under the design rules spreadsheet to get started. There are design rules for every type of element in this model, for beams, mat slabs, footings, all of the above. I'm going to flip directly to the mat slab tab and edit the values in here. First things first, I can choose to dial down the maximum bending and shear check if I don't want this designed all the way up to 100%. The program will do a very good job in some instances of designing things right up to capacity. So maybe I want to build in a little bit of slack by reducing that to, say, 90%. I can choose what I would like for my top and bottom bars. Let's say I would like number 8s on both. And I'm going to input values for my minimum and maximum top and bottom rebar spacing. And the program is going to iterate and find a number between these values that works for the given demand forces. I can choose what spacing increment it uses as well as it tries to use more and more bars. So let's do an increment of 2 inches. Top cover, bottom cover, side cover. I think I would like all 3 of these values to be 3. I can hit Control F on my keyboard, highlight or have highlighted multiple of them here, and input 3. Because let's say that these are going to be touching soil. And then I have my various options for the rebar design. I can optimize, which is saying that I don't particularly mind if it is a single layer, if it is going to be top and bottom. I can force mid-depth, top and bottom, or a single layer only. I'm going to choose optimize and let the program decide for me. Now I can set up multiple design rules for multiple different situations. For example, let's say that I want this to be my mat slab east to west rebar, and if I hit enter on my keyboard, it copies that line straight down, and I can make a new rule for my mat slab north-south rebar, just in case I end up wanting them to follow different rules. Right now they're a copy of each other, and that's fine. And then I might also want to insert a line specific to the pedestal. Go to the last tab here, and I can choose what parameters I want these pedestals to follow. Again, maybe dial back the bending check or not, and select the longitudinal shear ties. Let's change that cover value to 3 inches as well. With that done, I'm going to first go back and I can assign those design rules for the pedestals by clicking all three of them and finding over here in the design rule dropdown. Now I've got the three that I just input. Let's flip this down to be specific to the pedestal. That's another property that I could also easily define from within a spreadsheet. So now let's draw in the design strips that are going to define how the rebar is designed for the slab itself. Up here in the Slab Elements tab, we'll select Design Strips. The first input is the rebar angle from plan from the Z-axis, so let's do parallel to the Z-axis to get started. The number of design cuts is by default set to 50. This is the number of discrete sections that the program is going to look at along the length of this design strip, making cuts and tallying up the internal forces of the slab to use for the design. I might want to increase that number for a finer meshed solution, or maybe I want to decrease that number for a very short design strip that doesn't just need that many cuts close together. I'll leave it at 50 for now. And I'm going to select the east to west rebar and start drawing that. For this particular example, I'm pretty much just going to trace the outline of the slab that I already had. And I get this east to west rebar symbol here. Let's go back up, change the angle to 90. That will correspond to our north-south rebar. And again, just outline the whole slab. The design strip outline does not necessarily need to perfectly match the concrete outline here. It's completely up to the user. Once again, these are values that I can edit by way of a spreadsheet, the design strips spreadsheet. For example, I could change the orientation of one of these strips to a 45-degree angle, like so. I don't want to do that, but just for example, Control Z, undo, back to north-south. And that is all I need to do to take a first run at this reinforcement design. Let's solve the model again. I can toggle on the reinforcement right up here from the quick view and see the results. Zoom in a little bit, the text is overlapping, but I get for both the top and bottom in both directions, number 8's at 12. Easy to remember. I'm also going to want to review the pedestal results. I'm probably going to end up taking the worst case scenario from each pedestal and applying it to all three of them. Let's take a look at this in the table. So I have my unity check for bending, my unity check for shear, the governing load combination for each of those, and then what ends up being the actual reinforcement. So in this case, I can see that the worst case for vertical is 20 bars, 20 number 6 bars, and shear is looking at number 4 is at 10. For my slab reinforcement, there are a number of places where I can dive in a little bit deeper. I like to go to the design strip / cut results, a summary table of my east-west and north-south strip here. And again, take a look at the unity check for both the top bars, the bottom bars, and the shear checks. I see that in all of these instances, my utilization ratio is pretty low, 34%, somewhere in that neighborhood. So I'm curious what's going on with those. Let's right-click and select the detail report for this design strip. And I get an echo of the input values. I get diagrams for the envelope, shear, and moment values across that design strip. And I get the same summary of those code check values. If I look in the last line here, I see what is the controlling cut. So remember that this was divided into 50 individual cuts. This one is the controlling cut. It's cut number 16. Click on this for a little bit more information to see exactly what values were determined by the program. I can see in the summary that the top area of steel required by analysis was close to 4 inches. For the bottom was close to 3 inches. And then it was the temperature and shrinkage that controlled here. So that's why I got such low utilization ratios, is because this is a 30-inch deep slab, temperature and shrinkage controls. That doesn't surprise me too much. I'm okay with that result. I'm also going to want to explore my results visually. Let's go back to the color contour options and say, for example, turn on a moment in the X direction contour diagram. If this is my controlling contour, or I just want to know a little bit more about it, I can take a contour diagram cut. So let's see how this looks. If I choose a point and I'm drawing a cut line, let's say from edge to edge of this slab, now I get what looks like sort of a more traditional moment diagram across that cut applied directly to the slab that might help me understand a little bit more about what's going on. Hitting escape exits that tool, actually takes the contours away. Let's put the rebar display back on there. And a similar option, I can take a look at the design strip forces and kind of apply those same forces, or apply that same contour cut look, but I'd like to isolate, say, one of these since they're sitting on top of each other. Isolate that and kind of take a look at the force applied directly in the context of the model, so that I can look at that and say, yeah, this is where the moment is increasing greatly. It's right on the side of the pedestal there. I think that makes sense to me intuitively. And reset the value one more time. Back to our main display. If I'm happy with the results of my rebar, I'm ready to start printing reports and finalize this model. What I might recommend, though, is with strips that are this wide, the strip here is sort of as wide as it is long, it might be wise to investigate this in more discrete regions. For example, I have a model here which is the same model copied a few feet to the right, same loading and all. And the difference here is that instead of one strip in each direction, I've split this into 3 strips, sort of a left, middle, and right, top, middle, and bottom for each direction, because I'm curious to see if one section is worse than the other sections. Is it controlling my design? Do I want to consider having different rebar in different regions for this model? I ran it for the same combinations. When I look at the rebar results, it's a little bit cluttered over here, but I can see by and large I get the same results in each section. Top and bottom are both number 8 at 12, number 8 at 12, and this section is number 8 at 10s. Same goes with the east-west rebar. I get one section that is number 8 bars at 10s. So I'm going to want to investigate this further. Let's look at, say, this right side section detail report and make sure that nothing strange is going on here. I'm going to do the same thing I did before and investigate the specific controlling cut to see where those numbers came from. And I find that a similar thing is going on. Shouldn't surprise me that this section is really being controlled by temperature and shrinkage. The minimum enforcement required for that far outweighs the reinforcement required for the bending strength. So I believe what happened here is just that to meet that value, it needed to squeeze an extra bar into this 72-inch region. So I don't think that that is really an indicator that I need number 8s at 10 in that section. I think that using 8s at 12 all the way around is going to be perfectly acceptable. That concludes my mat slab design for today. For more information on RISAFoundation, please visit risa.com.